State University?
Yeah, so like Dr. Blown said, I'm Hamilton Carter. I'm from New Mexico State University. And what I'm presenting about today is our project to replicate Eugene Podkletnov's experiment from 1992 where he reportedly observed the Podkletnov effect. Okay. Thanks. So this is outline of what I'm going to cover. So we got it now. Cool. Whoa. All right. First, we're going to go through just a few basic physical principles that will make it easier to talk about the Podkletnov effect and his apparatus. Then I'll describe the original experiment. I'll talk a little bit about the status of our project so far. Then I'm going to talk about George Hathaway and his research team's replication attempt that was reported in 2003. And what I'm going to focus on there is kind of some of the difficulties that they ran into. Then finally going to talk about what we're going to do at New Mexico State regarding this project, and we're going to kind of take a step back and actually look at doing characterization of Podkletnov's apparatus before we try to go full speed ahead and build the whole thing out. And then finally we'll talk a little bit about the value we see in doing that. The three basics we need to cover, two of them are with relation to superconductors, and they're the Meissner effect and flux spinning. And then the last one has more to do with induction motors, and that's the rotating magnetic field. So the Meissner effect, put very simply, is that a superconductor, when it's cooled below its critical temperature, will expel all internal magnetic fields. It does that by setting up currents on its surface that create opposite magnetic fields to the magnetic fields coming in externally. Having said that, the next thing we want to talk about is actually kind of a violation of that, and that's flux spinning. In type 2 superconductors, you can actually get sites on the superconductor where a magnetic flux penetrates the superconductor, and it's then pinned in place by the superconductor. So if you try to move that flux away from where it originally penetrated, there's a force trying to move it back. And to kind of try to illustrate that, we'll see if this movie works. Can you start the movie from there? So are you actually in PowerPoint when you're doing this, or is it just?
No.
Oh.
Well, it is PowerPoint, but it's within the software that Adobe provides.
Okay, well if you put the pointer above the movie, you should see a play button.
It's exactly what you see there.
Cool. Okay, so I'll pantomime it.
It's floating around a little bit.
Yeah, so what you see in the bottom of the Petri dish, the dark disk is a YBCO superconductor. The shiny metallic cylinder you see above that is actually a permanent magnet. And I'm sure a lot of you have actually seen this demo before anyway. But what happens is that magnet is actually floating above the superconductor because the superconductor is rejecting its magnetic field, so you get this nice magnetic suspension that levitates that magnet. Now, the reason the magnet doesn't slide off to the side is because of flux spinning. So where the flux is penetrating that YBCO superconductor is creating a force that wants to hold that magnet where it originally started. And next slide, please. Okay, and then the third thing we need to talk about is rotating magnetic field. And this is something that Tesla and one other fellow developed independently in the late 1800s, and it's used as the basis for a lot of electric motors. And what you can see in this diagram is there's actually three electromagnets here. So you've got three sets of coils, the red, the blue, and the yellow. And each of those three is driven by a separate AC current. Those AC currents are 120 degrees away from each other, apart from each other in phase, and the net result is you wind up with a net magnetic field. So the magnetic field added up from each of these three sets of coils, that its its orientation rotates as the currents progress in time. And what the video next would have shown, but it won't now, is actually there's a very nice demonstration where you'd actually rotate or wrap three sets of coils on a toroidal piece of iron. They put a little glass plate over that, and then they take either a ferromagnetic material and put it in the center. And with the ferromagnetic material, the ferromagnet wants to align its field to that magnetic field, so it kind of chases it. You have two magnetic fields, and so you get a torque, and you'll see that ferromagnetic material rotate. Or they can actually just put a metal object in. And when they put a metal object in, what happens is that changing magnetic field, so the rotating magnetic field creates an induction current in the metal object. The induction current creates a second magnetic field, and again you have this torque between two magnetic fields, and at the end of the day you get rotation. And so it's pretty simple. It's actually what drives what is used in electric motors every day. And that finally brings us to the Podkletnov effect. So what Podkletnov reported in Physica-C in '92 was that he saw a small change in the weight of samples suspended above a rotating superconductor. And if we could replicate that, and if it's true, if it's what he thought was his hypothesis is true, this is going to be really cool. Because what he thought was going on was that the rotating superconductor was providing a gravitational shield. So far there have been a few replication attempts made, one by NASA that I'm going to talk a little bit about, and one by BAE, and one by George Hathaway. And they've all returned null results. Actually, let's go back to the cool. So this is Podkletnov's apparatus here on the right, a block diagram. And this is why we talked about the Meissner effect and flux pinning and rotating magnetic fields. Essentially what Podkletnov did was reverse that Meissner effect demo that I showed you. And so he has the magnet on the bottom in the form of a electromagnet, and then he's suspending the superconductor above that. Now that he's got his superconductor suspended, the superconductor is a perfect conductor, so he puts two electromagnets on either side of that to create a rotating magnetic field, and gets rotation of the superconductor through that rotating magnetic field. That's the basic premise of the apparatus. Okay, and next slide. In '97, Podkletnov published a second paper. And in his second paper, there was a lot more detail on how his apparatus was constructed, and it also came out that there were several variations that he had used of his apparatus. For these levitation coils, there were two variations. The one he originally reported was a pancake coil, a single pancake coil laying beneath the superconducting disk. Next slide, please. And the second variation was a number of coils distributed around the disk that appear to have ferromagnetic cores. Next slide, please. On the rotation coils, there were 5 different variations. Next slide. Thanks. And these are the 5 different variations here. The first one was a variation where he actually wrapped the electromagnetic coil through a hole in the center of the superconducting disk. And you can kind of see a side view of that here in this diagram. One thing to keep in mind is that in all of these diagrams, Podkletnov, and he documented this, omitted the another coil that would have been on the opposite side. So all of these diagrams they're actually should be symmetric. In the second variation, they put an indentation in a solenoid so that the superconducting disk could rotate through the center of the solenoid. In these two variations, what he has is a ferromagnetic yoke. So the ferromagnetic material, like iron, can actually steer the magnetic field through a magnetic circuit. So we have a coil here. We get a magnetic field generated through the coil, and then the magnetic field mostly comes out over here on the second pole piece. The same idea here with 2 coils. If you've seen a Zeeman effect experiment apparatus, it looks a lot like this. You get a nice uniform magnetic field between the 2 coils, and not much lost field because it travels through this ferromagnetic yoke. Then in this final variation, we've actually got the center of a solenoid pointed directly at the side of the disk. Next slide, please. This is another movie we're not going to get to see. Fortunately, it's kind of got the point where I can walk you through it here. This is from a 1963 movie made by Alfred Leitner that was talking about the effects of viscous drag and liquid helium. So that seems fairly unrelated, but in watching the movie, we realized that his apparatus is very similar to Podkletnov's, at least in the rotation field sense. These 4 little black tubes are actually electromagnets. Within the liquid helium, he has a copper cylinder, and what he wants to do is rotate that copper cylinder so we can test the effects of viscous drag between the copper cylinder and the liquid helium. And so it's just exactly like that last variation in Podkletnov's apparatus. He's got his rotating magnetic field set up with these 4 electromagnets, and the copper cylinder just spins up nice as can be. Next slide, please. So that's kind of Podkletnov's apparatus and this experiment. Where we are at New Mexico State, we contacted NASA Marshall Center and asked them if we could borrow the equipment that they had used in their 1997 replication attempt. And they were very kind and did let us go ahead and borrow the equipment. So it's taken about a year to get the loan through. But we got the loan through and we took possession of the equipment in December. We're starting our laboratory next week, so we'll get the equipment moved in next week. One of the nicest things is we actually got the superconducting disc that they used. One thing that I left out in Podkletnov's description of his experiment was the superconducting disc, as far as solid single ceramic superconductors go, was fairly huge. It was about this size. And so NASA actually went through a lot of effort just to make that disc. And so we've got that, and that gives us a good starting point. We're currently funded by the New Mexico Space Grant Consortium, which is an organization that's funded by NASA. It's just a little starter grant, basically to look for more grants. So it pays my grad student salary, which is very low, and it's got a small budget in it for some liquid helium and liquid nitrogen. And that runs through June. We sent off a grant to NSF, although we're not real hopeful that that's going to come through. Next slide, please.
I might mention that Paul Werbos, who will be presenting around 2 o'clock
Mm-hmm.
remotely from NSF, might be a good target for you.
Okay, cool. Thanks. Awesome. Good to know. So George Hathaway and his research team in 2003 tried to reproduce the Podkletnov effect. I was lucky enough 3 weeks ago to go up to Toronto and visit the lab. They're super nice guys and very impressive lab. And this is their apparatus. What I want to tell you about really is some of the difficulties they ran into trying to replicate Podkletnov's apparatus. Next slide, please. The first problem they ran into was actually getting the superconductor to levitate. As I mentioned, it's actually a fairly big disk, as Podkletnov described it. They communicated with Podkletnov, and he said they could use a smaller disk, so one about this size. You still need a substantial magnetic field to levitate that, which isn't too big of a deal as long as you're working with permanent magnets. Podkletnov added one extra ingredient to the mix and said that the sweet spot to run this electromagnet at was 100 kilohertz. So now you've got an electromagnet running at 100 kilohertz with a fairly large field, which is actually fairly difficult to do. And so what Hathaway and his team reported in their Physica C article was that at 60 hertz, where they were able to use a iron core in their magnet, they could get enough field to levitate a melt textured disk in liquid nitrogen. But above 100 hertz, they couldn't get that to work. So then moving to 5,000 hertz and liquid helium running colder, they were able to levitate a fine powder YBCO disk, which was progress, but it still wasn't good enough per Podkletnov. Podkletnov told them they needed to levitate with at least 50 kilohertz in the levitation coil, and that it had to be a coarse powder YBCO disk. So they were unable to levitate the disk as Podkletnov specified. Since they weren't able to do that, they suspended the disk in the apparatus using a metal shaft, and they attached that metal shaft via a pulley to an electric motor to provide the rotation of the disk. So they did still have the levitation coils, and they did energize those levitation coils with 100 kilohertz frequency. They also had the rotation coils, and they energized the rotation coils as specified per Podkletnov with between 2 and 3 megahertz per frequency. They got a null result. The rotation coils, interestingly enough, were doing something because they did create enough of a torque on the disk that at one point they actually stalled out the exterior electric motor. So they were creating a rotational force. So that's good. Okay. So now we're on to what we're going to do at NMSU. So one thing we learned from background research and talking to George is that constructing the apparatus from the ground up as Podkletnov specified is very, very difficult. So what we want to do is back up and ask some simple questions first. We want to ask, how does the levitation coils work? How should they work? What should we expect? And the same thing about the rotation coils. And what we want to do is back up and characterize simpler apparatus with respect to input frequency and voltages and stability of levitation. Next slide, please. So I'm the graduate student on this project, and that makes a big chunk. Basically, I do all the background literature searches. And so this seems simple enough at first. Lots of people use superconductors for magnetic bearings. It's a nice, almost frictionless bearing because you can suspend a magnet above a superconductor. Life is good. So I thought, okay, we'll go look through the background literature. We'll figure out how people do this. How hard can it be? Well, it turns out nobody does it at 100 kilohertz. For maglev trains or mechanical operation, you don't need to run at that frequency. They run at DC frequencies. So data hasn't been compiled that we could find on how you should expect a levitation suspension to work at those frequencies. Next slide, please. So what we're going to do is kind of two stages. We're going to use the NASA disk, and we're going to test it for viability using a permanent magnet, which kind of has nothing to do with this. Superconductors degrade over time. The NASA disk was actually hermetically sealed, so we're hoping it hasn't. But we're going to use the levitation above a permanent magnet as a good first viability test. If it levitates, that gives us a good feel that we know we got some kind of superconducting currents going, and if it doesn't, might have to do further tests. As far as the actual levitation characterization, we're going to back up and use small samples for that. We don't want to use this big disk where we can actually dump it down on itself and crack it before we even get started. The other nice thing about using small samples is they require a smaller magnetic field to levitate, so it's not as hard to get a high frequency field if it's a smaller field. And what we want to do is characterize the levitation height and stability versus the input voltage to the levitation coils and the input frequency to the levitation coils, and if we can, also versus the temperature of the disk. A team in Russia already did part of this work, but again, what they were looking at was things like maglev trains. And so if you want to run a maglev train and your train develops a wobble, you want to make sure that the train doesn't come crashing down because you developed a wobble. And what they saw was they measure between DC and 700 hertz, so fairly low frequencies. And there is actually a place where the levitation will become unstable. And for their samples, it was around a couple hundred hertz. And what's going on there is essentially you're breaking the pinning sites that we mentioned earlier. And so you're creating a wobbling force, and they found out that this frequency really has more to do with the size and mass of the superconductor and its pinning field strength. So below, in other words, if you've ever seen like a Tuskegee bridge video where that bridge had a resonant frequency it wanted to vibrate at, it's the same idea here. So as they moved the frequency lower, they had stable levitation, and as they moved the frequency higher, they had stable levitation. But they only went up to 700 hertz because that's all the higher frequencies they could ever imagine needing. Next slide, please. So I had a similar experience with looking at how the rotation coils might work. People have been building superconductor motors for over 20 years now, and so this picture here is actually a huge superconducting motor that they built in Massachusetts for ship propulsion. So again, it seemed like this should be an easy thing to figure out. Next slide, please. But again, we ran into kind of the same problems almost immediately. Podkletnov says that he runs his rotation coils between 2 and 3 megahertz. which nobody does with the superconducting motor. So again, there was no data to tell us how these should work. The next thing we wanted to do was kind of analyze them to see, next slide, to see if, is it an induction motor, and if it is an induction motor, well, this is great. We can just do a simple induction motor analysis, see what the supercurrents look like in the superconductor, and maybe that will tell us something. And what we found out pretty quickly is that's not an easy question to answer either. We contacted one scientist who's kind of an expert in superconducting motors, and for example, this coil configuration, as far as he knows, has never been used in a superconducting motor. Next slide, please. So kind of what we're doing is we really want to, when I said we're going to test viability, we want to build up these coil configurations and see if we can get them to rotate the disk at any frequency. And then after that, see as we step the frequencies up if we can continue to get rotation, and document what we see as far as speed and acceleration of the disk in the various rotation schemes, again versus frequency, input power, and temperature of the disk. And so what you can see here is how we think this coil configuration works. So I got to learn not to point at the screen. What we see is for example, if the coil current is going across the surface of the disk from centered outward, that should induce a magnetic field. We should get an electromagnetic field this direction. Via the Meissner effect, we're going to get a supercurrent running in the other direction, and an associated magnetic field, and they should repel each other, and with two sets of coils we should get a torque. We just want to verify that and characterize it to see what we're up against. Next slide, please. Back to this arrangement, which was in the video and which was that last arrangement. This actually has been built. It looks like a lot like a documented hysteresis motor. And so this is actually kind of an interesting thing that I talked about it a little bit earlier. Hysteresis motors were some of the earliest motors in that what you do is you take a ferromagnetic material, place it inside a rotating magnetic field, so that's the blue arrow. This ferromagnetic material wants to align its magnetization with the rotating magnetic field. Probably can't do that anymore. Okay, so now a nice red arrow should appear parallel to the blue arrow. Hey, that worked. Awesome. Okay, cool. But as the rotating magnetic field rotates away, if you could hit it one more time. Thanks. Again, we wind up with this magnetic dipole and a magnetic field at an angle to it, and so we get a torque between the two, and the ferromagnetic material will rotate. The ferromagnetic material is trying to reorient its field to match the rotating field, but it can't keep up because of hysteresis losses. They've done the same thing in superconductors, where they actually create, essentially what you see in the diagram here is the magnetic field is creating pinning sites on the edge of the disk and then sweeping away. And again, these pinning sites are exerting a torque on the disk and trying to keep up with that rotating magnetic field. So this is good, and this is actually where we see some of the value in what we're trying to do. Next slide, please. So as far as theoretical value goes, the theoretical papers I've been able to find on the Podkletnov effect, the vast majority of them start out from basics. They start with a superconductor and ask the question, given a superconductor and what we know about superconductors, is there anything inherent to a superconductor that could create a gravitational shielding effect? What we'd like to do by characterizing how these different winding configurations work is provide future theoreticians with information like this that says, well, okay, now you've got a little bit further along jumping off point. If you had a superconductor and a field that looks like this, or if you had a superconductor with pinned flux and a rotating field dragging it, does that give you any better place to hypothesize from? So that's where we see the value theoretically. Next slide, please. And experimentally, what we're hoping to do is characterize where the difficulties in getting this apparatus to work occur on a smaller scale, looking for solutions to how we can make it work on a larger scale as Podkletnov documented. Next slide. So in conclusion, we had the equipment from NASA. We have funding running through June. We're going to back up and actually study how the apparatus works with regard to the levitation and rotation parts of it. We think there's a theoretical and experimental benefits to that, and it puts us in a good position to build, or a better position to build a completed apparatus in phase 2 of our project. That's all I got. Yeah.
Why do you think the other 3 replications didn't work, and is there a justification for using 100 kilohertz?
The justification I know of is in 2 of the cases well, actually the one case I definitely know about. In Hathaway's case, they asked Podkletnov, what frequency do we have to use to make this work, and he said the sweet spot is 100 kilohertz, and below 50 it won't work.
Why?
Yeah, he didn't offer any explanation that I'm aware of. Yes.
How come there was experiments where one did it in 5,000 kilohertz and worked once and it didn't work the second time?
Can you back up to that slide, please, Dr. Lewis?
Which one are we going to?
There was a table early on, so it's probably 10 slides, 15 slides back. My guess is it was 2 different disks. Here. So what it shows is liquid helium at 5,000 hertz. With a fine powder disk, it did work. At greater than 5,000 hertz, it did. And I assume they were trying to do the same thing that we did. You know, well, what level can we get this to work at? And once we get it to work somewhere, then can we work our way out? So, yeah.
Have you thought of using the supercurrents to feed back into the system through the coils?
Or you were talking about the suspension coils? Yeah. One way that we've thought of to get these fields is actually to use a superconducting magnet below the disk to try it, because it takes it should take about 1.5 Tesla. And again, you still have this thing where it shouldn't be too big. Yeah, we thought about it. We'd have to get a superconducting magnet, and there's still a lot of energy to flip back and forth at 100 kilohertz. So the driver at that level is also an issue.
How much power after that take?
Off the top of my head, I don't know. I can tell you when I went up and visited George Hathaway's lab, they were driving 100 kilohertz, I believe at a kilowatt into their levitation coil, and it was interesting. The impedance matching network sat in a crate, this tall, standard instrument bin, and used every bit of it just to handle that much power and match the impedance between the driver and that induction coil. So.
Now, why did you choose the rotating superconductor as opposed to the rotating field? Didn't you have a later paper, 2002, with the rotating field?
I'm not aware of it, if you did. No, so he's had, there are 2 Podkletnov effects that I'm aware of. One is this one where he had the rotating superconductor. And to be honest, the reason we chose that one is because that's the one I knew about first. I didn't know about the second one until much later. The second one was the gravity impulse beam.
Exactly.
Okay, yeah. In that one, the superconductor is actually stationary, and they essentially use it as a cathode in a rather large electron gun. And like I say, well, there's 2 reasons. I found out about the first one first. The second reason is initially that the first one was published in a refereed journal, so it seemed more viable, whereas the second one wasn't. Yes, sir.
What's Podkletnov been doing for the last 20 years, and where is he doing it?
Apparently, and this is all information I have from the web and talking to folks, so who knows how accurate it is, but what I hear is he went back to Russia, so he's been doing it there. He went back to Russia in '96, so that '97 paper was pretty soon after he returned. And what I hear is he's been working on this and mostly lately on the impulse generator. And when I was here last year, somebody told me that he's taken a company private and has kind of cut off communications with everybody until that company works out.
I got an email from him less than a year ago, and I reproduced that email on our report on the impulse gravity generator, which is available at our bookstore table as your magazine. But it's exactly the story. And he says the commercial direction has been successful, and that's why he's cutting off.
Cool.
Thank you very much. And let's
Thank
move
you.
on.